Hi, welcome. I'm Dr. K. Nimala, working as an associate professor in the Department of NWC in SRM IST. Today, I just want to discuss about large language models. So, whenever you talk about this large language model, you normally shorten it as tell it as LLM. If the technical jargon feels overwhelming, think of an LLM as a ultimate digital copycat and a predictor. So you normally tag LLM to be a predictor or a copycat that literally predicts the text. It could be a character, it could be a word or a token. It try to understand what would be the next token and accordingly generate text. So what is large language model? Large language model is the one, as I said earlier, it is an LLM that predicts a token or a long sequence of tokens or continue with a piece of a text or a character. So, in general, a token can be a whole word or a subword or even a single character. So, this large language models, you can always, take an analogy with a smartphone feature. Like when you type a text in the smartphone, that I'm running late for, it automatically, fills the space telling that it might suggest that whether you're running, I am running late for school or work or, you know, as per the context that I converse with. So this LLM is is being compared with the smartphone feature, and it doesn't actually know facts the way a human does, but it based on a statistical probability, it fills the word that would come next based on everything it has ever read. Okay, so it takes the knowledge from various websites, books, articles, Wikipedias, and all that. So whenever you talk about LLM, why LLM outpredict older models? See, when you talk about LLM, it is nothing but a large language model. So it tries to outpredict older models because LLMs have got far more parameters. You have the parameters of LLM to be in billions of parameters, and all these work together to predict the next text that it is to come next, and it is far more context, meaning that LLMs gather and weigh a large span of surrounding text before predicting the next token. So it's like, for example, if you ask an LLM what color is the sky. See, as humans, what do? We just look outside and tell that okay, the sky is blue, and we fill that the color of the sky is blue. But actually the LLM, since it's a predictor, it simply knows that in millions of books and websites the word sky is frequently followed by the word blue. So LLMs would fill that the color of the sky is blue. Okay, so this is how it works. So this is the concept behind LLM. And when you talk about the working of how LLMs work, they are the most basic LLMs are statistical pattern recognition and prediction systems. So through a statistical probability, they try to compute for the next word, at what should come next based on everything it has ever read. So through statistical probability, it tries to recognize the pattern and accordingly predicts. So when you talk about LLMs output the next likely word or the token in a sentence, or the token could be, as said earlier, the token could be a unit of text, it could be a word, it could be a character, or it could even be a sentence, paragraphs, or books, which is based on context. So when you talk about ChatGPT, Claude, Perplexity, and all other AI generative tools, they all input, based on the number of tokens, and they use different parameter volumes for generating the next word. So the likelihood of the next work appearing is determined by next work or next word is determined by the context in which the words are seen in a large body of text, that is the corpus, and the input to the chat. So in general, LLM uh, goes through two main stages. One is the pre-training, stage one, and stage two is fine-tuning. So under pre-training first stage, it feeds billions of pages of text from internet, books, articles, Wikipedias, some public forums and all that. And accordingly, it learns the grammar, the structure of the sentence, the facts and all that from all other sources. And in the second stage, what it does is it uh, comes with fine tuning. That is, it gives a helpful, polite, and accurate response based on its learning. So, under stage two, it tries to fine tune the responses. So, when you talk about LLMs, they understands the meaning and all that. It is nothing but learning from a large corpus that allows LLM to understand the meaning of words. So here you talk about large corpus that comprises of books, articles, internet sources, Wikipedias, public forums, all digital repositories. You tell it to be a large corpus. For example, the training data may consist of many sentences beginning with my favorite color is. Okay, so uh, the next word will be a color, allowing the LLM to cluster the words that is red, blue, green into a set that represent the concept of colors. So it is like based on various sources corpus, it automatically predicts the next word to be the different colors. That's how it works. So it is important to know that LLMs don't really understand anything. They don't understand like human, but they mimic as a human, and they simply predict the next token based on the facts that is. Okay, so it doesn't have emotions, it doesn't have feelings, it doesn't actually get as humans do, but it mimics the behavior of a human by getting the facts, the pattern from the corpus that is already there, that is already that the model is trained for. So they create the statistical patterns that groups similar tokens based on a complex measure of how similar or dissimilar they are. So it just fills the next word, next sentence based on the similarity measures. Based on the similarity measures that we will see it in the next thing. So whenever you talk about LLM, the data that is used to train LLMs are in an unsupervised manner on a vast quantities of open sources and licensed data. That is the data corpus could be from web, papers, patents, books, any of the digital repositories. It could be from a common crawl or it could be from any other, repositories or the corpus. So the responses are refined using a question response pairs, that is from the web or the human or bootstrap. So you talk about the responses that are refined using question response pairs, and the concept behind this reinforcement learning with human feedback is used to reward LLMs to give appropriate responses. So it is self learning. It's a self-learning mechanisms that has been adopted in LLMs where they get the feedback based on some rewards and all that, and accordingly rank the response and accordingly fill the next words or the tokens. So you talk about the next word prediction. So when you talk about the next word prediction, it is influenced by the frequency the word is seen in various contexts. Again, it depends on the similar pattern, the statistical probability. But there is a degree of randomness so that the word with highest probability isn't always seen. So when you talk about the next word, it's again based on the statistical probability. So that next word would be a one which has got highest probability. So it automatically fills the next word by its probability values. So suppose for example, my favorite color is, all the colors come in that. Green is one color, red is one color, pink is one color. So based on the colors and based on the probability values that has been thrown, here pink ranks highest probability with around 11.6 percentage. So pink color would be my favorite color. So this is how it tries to calculate the next word prediction. So when you talk about the meanings can change based on the context. See, the LLMs are context oriented. So, meaning that the same word could appear at different places and it would change over time. For example, gay is a word that comes at different places with different contexts. So, accordingly, it tries to fill in the appropriate word that that goes with a similar context for a sentence. So here is an example to tell about the word gay, the word broadcast, the word awful. So with this kind of computation, it tries to fill the next word in a sentence or a next character, um, or a next paragraph and so on. So when you talk about LLMs can be creative. Creative in the sense, even though it cannot think like a human, it could seem to be creative. We'll see how does it work. So a consequence of context-based learning and randomness allows the LLMs to generate surprising outputs. So whenever you note though they are not creative in human sense, but driven by pattern recognition and prediction algorithms. So the creativeness is again based on the pattern recognition and the prediction algorithms. So we can make LLM to be creative based on the higher prediction algorithms that we are trying to incorporate. So they are, in other words, we could always tell that it is the LLM that they are not conscious about. They don't have feelings or awareness, or they do not have thoughts. They do not have opinions, beliefs, and consciousness. But they are the software that run on a massive computers with billion parameters, and somehow or the other they try to predict the next word, the next token. So we can use LLMs to identify weakly similar concepts from different disciplines and help understand different disciplines. So you can have LLMs to be the one that uh, can understand different disciplines, generate diverse narratives, help with ambiguity. That is like it to some extent it helps the ambiguousness in a text, and even we can have the role play. Whenever you talk about LLMs, they can hallucinate. That is the limitations. Anyway, we would see it how in the limitations of LLM. The general working of the LLMs, it is again based on a transformer model. So what is a transformer? It is nothing but we nowadays talk about transformer models and all that. So it is nothing but a state of art architecture behind translation, summarization, chat, and most modern language applications. So LLMs are purely transformer based translators. That is, a transformer-based translation application is what an LLM is. So you can input a given sentence, and you can even go for a translation, or you can go with a summarization of the text, or you can have a kind of a question answer chat with LLMs. So it is nothing but a transformer. The architecture is a transformer, and the transformer architecture is again categorized into two types. One is encoder and another is a decoder. So when you talk about encoder, it is the one that converts input text into an intermediate representation. So an encoder is nothing but an enormous neural net that processes the source sentence. So encoder is the one which converts input to an intermediate representation, and a decoder is the one that converts that intermediate representation into a useful output text. That is an enormous neural net that generates the result. So LLMs are based on transformer based architecture which involves encoder and a decoder. So the transformer architecture could be an encoder type, or it could be a decoder type, or it could be a combination of an encoder and a decoder together. So a full transformer chains both halves, that is the encoder that reads the input and the decoder that writes the output. So if you look into the architecture of a transformer based architecture, you give an input, it goes to a transformer based translator where encoding and decoding happens and you get an output. So here the input is fed into the encoder. So the encoder, it processes your input text, that is I am a dog, and it gives into a intermediate representation. So here the representation, what it does is it captures the relationships and context across the entire input sequence. So the decoder in the transformer based translator, it converts the representation into the output text. So here the equivalent French sentence for I am a dog is being output at for this particular example. So as I said earlier, the LLMs could be a transformer based architecture where it can do a translation or a summarization, or you can have a kind of a question and answer, or any other kind of an application. Here we use transformer, the LLMs, to be a one that acts as a translator where it converts your English into a French sentence. The core mechanism of LLM needs to be understood with a concept called as self-attention. So we would have come across this kind of self-attention mechanisms and neural networks and all that. So transformers, they rely heavily on the self-attention. For each input token, self-attention asks one question. That is, how much does each of the token of the input affect the interpretation of this token? Okay, so the self here in the self attention refers to the input sequence. So under self attention, it only weighs the relationship between the tokens within that same input, not to an output or other sequence. So when you talk about self attention, it actually computes the weights of the relationships between the token, and accordingly it gives the interpretation of this particular token. So, when you talk about the working of a transformer based on self attention, here we could go ahead with the step by step process. That is, you try to assume each token is a word within a single sentence of context, number one. The second is every word compares itself against every other word in the sentence. So under each comparison, it produces a relevance or attention or a kind of score. And based on the high scoring words, shape that token's representation more strongly. This gives a clear snapshot of how the next word interpretation is being predicted. That is, like you when it's given a single sentence to a transformer model, each token in that sentence, that is a word, it captures the token, it captures the context, and for every word, It compares itself against with every other word and computes a kind of an attention score or relevance or a rank. And with that comparison, the high rank or the high scoring words would be considered to be the token's interpretation most strongly. That is the next word, is what the computation is. Self attention in action, resolving it. Here we could go with an example. The animal did not cross the street because it was too tired. So the pronoun here, it refers to animal or the street. So it is a quite a little ambiguous. So the self-attention scores the relevance of every nearby word to it and finds animal more important than a street. So if we just look at this input sample, that is the animal didn't cross the street because it was too tired. The it here denotes whether it's an animal or a street. But when you just check with the self-attention score, the score is more relevant to the word animal than the street. Okay, so animal scores higher value. Okay, so if the last word changes to too wide, instead of to assume that the sentence, the last word is instead of too tired, it is too wide. So instead of too tired, if it is too wide, so the self-attention shifts now from street outweighs the animal, and the it here refers to the street. So the mechanism is context sensitive, so not fixed. So the self-attention takes care of providing the scoring based on its context. And that's how the next word is being predicted or it is being weighed. I hope you understand this particular concept. Okay, moving to the self-attention, there are different types. Like you have this bidirectional versus unidirectional attentions and all that. So the self-attention mechanism differ in which neighboring token they are allowed to consider. So encoders use this bidirectional, or they can and most probably decoder uses unidirectional. So when you talk about this bidirectional attention, they calculate the relevance scores using tokens both preceding and following the word being attended to. So it is like bidirectional attention is most probably used in encoder type of transformer, and unidirectional attention are being computed in the decoder of a transformer model. That is, under unidirectional, they can only gather context from tokens on one side of the word being attended to. So, for example, the previous sample we saw it in a sentence. When it is a bidirectional one, you calculate attention scores or the relevance scores either side of that particular word in both the directions of the word hit. And whenever it is considered to be a unidirectional, you always concentrate on the tokens on one side of the word. I hope you understand. So it is when you talk about bidirectional attention, it is best for generating representation of a whole sequence. But whereas a unidirectional attention, it is required for applications that generate sequences token by token. When you talk about self-attention, we spoke earlier about self-attention. Now let's move on to multi-head or the multi-layer self-attention. In multi-head self-attention, each self-attention layer is made of several heads. That is, you try to go with a complex mode. In multiple head layer self-attention, your self-attention is calculated in each and every layer. So you have each heads parameter start at random values. Different heads learn different relationships between words. So for example, you learn the words, in different ways, with the different relationships between words. That is, you talk about pronoun resolutions, you talk about grammatical relevance, other word interactions, and all that, and you put all that understanding, combine all its heads, and you try to calculate a weighted average or a dot product of it and give one result. Meaning that a multi-layer self-attention mechanism in an LLM talks about the collective different layer heads. They compute in a different perspective the scores by pronoun resolutions, for example, grammatical relevance, and other word interactions and all that, and they compute and weighted average, and based on the weighted average they come with one token predictions, and accordingly they try to you know give a response for that input sample. So here you have layer stacks depth build, meaning here you talk about multi-layer, no? So you talk about different layers. So you talk about deep layers, you talk about middle layers, and you talk about earlier layers. So in the deep layers, you focus mainly on the sentiment, context, thematic links across the whole input. And in the middle layer, you talk about how do you integrate earlier signals into more concept oriented, and in earlier layers you talk about the basic syntax and local word relationship. That is, you compute the attentions from different attention heads based on different concepts that you segregate based on layers. So the output from each layer becomes the input for the next. So it progressively learns, or it abstracts more understanding for the given input. So why are transformers so large? You talk about LLMs as large language models. Why it is so large? Because transformers, they contain hundreds of billions or even trillions of parameters for their architecture. So meaning that it is large. So you talk about the general principles. Whenever you talk about large, you need to little focus on know about what a smaller models principle is. Actually, when you talk about smaller modules, might be it uses fewer resources or fewer parameters in their architecture, and their responses, the prediction is also low, and the cost is also less when you compare with the large language models. So, when you talk about how LLM generate, as said, LLMs are essentially autocomplete mechanisms. So they can predict thousands of tokens at once, not just one or two. So an example is here is another example that generates the probabilities for what fills the mask. That is, given an input sample, my dog Max knows how to perform many traditional dog tricks. So, what what is that? What fills the mask? The dash. That is, the many traditional dogs. What they do, they can sit, stay, and roll over, and all that. These are the activities of a normal traditional dogs. So the filling here in that particular input sentence could be it can sit, stay, and roll over, or it knows how to sit, stay, and roll over. So when you talk about the probability computations and all that, he can sit, stay, and roll over has got higher probabilities, that is 3.1 percentage, meaning that it the the blank that it fills is he can sit, stay, and roll over. So when you talk about from mask to conversation, a user's question is the given sentence. So the LLMs, they reply is imaginary mask it fills in. That is, as I said, LLMs are nothing but a copycat or a predictor. No, it just computes mathematically and then tries to fill an imaginary mask for a given sample. So in general, you can tell LLM is an hyper intelligent mirror of a human language. That is, it reflects back the knowledge, the pattern, and the style of human writing, allowing you to brainstorm, write, and learn faster than ever before. So, what is if the user question is what is the easiest trick to teach a dog? So, what would the LLM respond? With the max reasoning, it will generate the probabilities for the response for this particular user question and it auto completes a word problem prompt. It just fills accordingly based on the probability values. So when you talk on or understand the benefits of LLM, LLMs can generate a clear communication. That is, it makes you to understand the text easily for a wide variety of target audiences. The second point is strong on trained tasks. So LLMs make reliable predictions on tasks they are explicitly trained on. Is the second benefit. And the third is debated generalization. Some researchers, what they claim is LLMs generalize to inputs they weren't explicitly trained on. Others refute this claim. There is always a debate, talking about the generalization concept. Usually LLMs tend to generalize the inputs when they are not trained for. That is one, benefits that they always give a response. They don't tell that they don't know. They try to generalize it even on the explicitly trained ones. So when you talk about the problems or the challenges with LLMs, even though there is quite more benefits of LLMs, they the when you segregate the model's life cycle, that is training and predictions. The problem with LLMs are in training, they gather an enormous training set. They learn from various digital repositories. So training takes time. Automatically, it leads to cost. Okay, so that is one disadvantage. They can consume months of time, enormous compute and electricity. That is again the drawback of LLM. They solving parallelism challenges across hardware. When there is an hardware reliability constraints, challenges are more. And when you talk in the terms of predictions, what are all the drawbacks or the challenges? You could say that they try to hallucinate. Okay, they will hallucinate in the sense they will sometimes confidently make up fake facts, fake codes, or wrong answers. They are actually speaking, they are not lying, they are just guessing incorrectly based on the maths. So the hallucination is one drawback. The second drawback related to inference predictions is they use enormous uh, cost, enormous compute and electricity per inferences. So they try to go with large more training resources. So the bias here, like all ML models, LLMs can exhibit all sorts of biases. So this could be a quick recap of the big picture about LLMs, what we have seen in today's video presentation. So beware, LLMs may seem to lie and hallucinate. So accordingly, you try to um, understand it. And training data, so bias in learning, search, and probability. Don't believe the outputs, they always need checking, at least for now. So LLMs are not humans, they are not people, they have no intentionality. So try to be aware of LLMs. So interacting with LLMs using prompt engineering. So for interacting well with LLMs, you need to do a correct prompt engineering. That is, it means that you need to tailor your questions and accordingly input to your LLM so that they give a correct response. So prompts can take many more forms, that is instructing the LLMs to take on a role as a teacher or a pirate, and the guiding the way it should process its output. So you can go for any of the prompt techniques and accordingly feed it into LLM and get the appropriate output. So LLMs can help you engineer prompts. So you may not know how to ask an LLM to do the task. You might ask it to, how to ask an LLM to do a task. So there are a lot of prompt techniques. That is all related to prompt engineering that we'll see in the next video.